Okay, you guys can see my screen now. Hello?
Yes, sir.
Yeah. Okay.
Yes, sir.
Yeah. So let's begin. This is the AFS-I lectures, Pune, Topology week 5. It will begin this year and end next year, quite a long week. So today is Wednesday 29. First item is to review the PDF file of the last lecture and to answer any questions you have about it. I should remember to point out that in the last lecture, there is a correction. In the last lecture, I told you that complete plus totally bounded implies compact by 20 questions argument. And then I also say that one can prove this using tight extension theorem. That doesn't make sense to me. Looks wrong. So stick to the first 20 questions argument. Okay, so let's go and look at those notes. So this was 22nd December. And we began by saying compactness is a generalization of the notion of finiteness, as well as certain basic subsets of Rn, namely disks and other closed bounded sets. We recall the definition of compactness for a topological space in terms of open covers having finite subcovers. But as I told you, what is going to be important for us is compactness for metric spaces, because that intertwines with properties of the metric. This is more than what one can say for topological spaces. There are some more theorems. And to familiarize yourself with this, best way to do is to solve exercises in Kumaration's Topology of Metric Spaces, Chapter 4. I hope you had a look at it. When you have your tutorial sessions, you can try some of the exercises there. Tutors should pay attention to this, because I think they have an opportunity to use the tutorial hour by solving exercises from such places. Okay. So starting term in compactness is every open cover of the interval 0, 1 has a finite subcover. That inspired the definition of compactness. And that is proved by the 20 questions argument. 20 questions really means any number of yes, no questions. So if the interval has an open cover which does not have subcover, you ask, okay, so which half does not have subcover? Because if both halves had finite subcovers, then all of it has. So take that half. Now cut it into 2 and ask the same question and go on narrowing and narrowing and narrowing it. And those tinier and tinier nested closed intervals, if you look at their centers, they form a Cauchy sequence and it converges. That's where this interval being complete is very important. All compact metric spaces turn out to be complete. Anyway, we already know how to prove real numbers are complete. They are the completion of rational numbers. One of the constructions is that. And then that point is definitely in some particular open set. And so any tiny enough interval around it is in that open set, contradicting this 20 questions choice of those intervals. So that shows this as finite subcover. And so that leads to the HighInBorder theorem. Every closed and bounded subset of C also has this property, is compact. Because being bounded, it is inside some such box. And any closed subset of a compact space is compact is a topological property, which we proved. Then we said that in any metric space, a compact set is bounded with respect to the metric. Of course, closed and bounded with respect to the metric. Here was that. Okay. Then we defined the notion of a limit point of a set. A limit point of a set means every punctured neighborhood of that point X has some element of A in it. And then we came up with various equivalences. Okay, we stated various standard equivalences of compactness in the context of metric spaces. This first one is purely topological. But there are other properties as complete and totally bounded, which are metric properties. And how did the implications go? 1 implies 3, 2 and 3 are equivalent, 2 plus 3 imply 4, and 4 implies 1 by 20 question argument. This is how the arguments went. And we explained this totally bounded concept by means of mobile towers and their range. And then came this statement which I am saying looks wrong. Forget this. To reduce 1 from 4, we can use tight J extension theorem. No. What I have earlier said, stick to that. The 20 question argument does it. Then every continuous function on a compact metric space is bounded. How? Conversely, if every continuous function on a metric space is bounded, then show that it is compact. This you have been asked to prove. One way compact means image is compact in real numbers, which means it is bounded and closed. So every function is bounded. Now you are given various exercises, which I hope you have looked at, you have done, I don't know. And then we shifted to the Euclidean space with the Euclidean distance given by the Pythagorean formula. And I asked you to show that any distance preserving map from R2 to R2 is a bijection. And I asked you how to write it. And then what is the group of all distance preserving automorphisms. And I think by now you guys have solved it using linear algebra, etc. First, you have to make sure that the map is linear. And a linear map, first of all, has to preserve lines. So here was the betweenness argument that shows it preserves lines. It also preserves angles, it preserves tangles, etc. It preserves parallelograms, so it preserves vector addition, etc., etc., etc. You can show it's linear very easily, and then your linear algebra can come. Okay, the next lecture after that was about families of functions. So first we talked of continuity at a point, then continuous everywhere, and then uniform continuity. Now at this point, you guys can hear me and are able to see the board.
Yes, sir.
Okay. So we introduced the notion of uniform continuity for a function, which means the same delta works given an epsilon, the same delta works wherever you are in the domain. And we gave examples of functions which are not uniformly continuous. Then we said if your space is compact, then any continuous map is uniformly continuous. And here was the proof. After that, we started looking at families of functions. These are families of functions within two metric spaces, though the case of importance for us will be when y is real numbers or complex numbers. We are looking at functions. We want to apply such things to families of functions. But many of the theorems you will see do not need y to be r or c. You can see from the proof. And so the arguments will remain valid when y is a metric space, or sometimes you will need y to be a complete metric space, because one of the properties of R that you will use is that it is complete, same with C. Now, given a set of functions going from x to y, we say it is equicontinuous at a point. If given an epsilon, there is a delta which works for all functions in f. And so for any other x prime which is close enough by delta, the distance is close enough by epsilon. Uniformly equicontinuous means if distance between x and x prime is less than delta, then the distance between fx and x prime is less than epsilon for all f. So this delta doesn't depend on f because equicontinuous. Uniformly means it doesn't depend on x. So it depends neither on x nor on f, neither on x uniformly nor on f equicontinuous. So that's uniformly. And then you're given some simple exercises which are basically checking definitions. Except this one, if x is compact, then any equicontinuous family is uniformly equicontinuous. That you will see quickly. Today also I will remind you of the proof. And then there were some other stuff which I didn't follow up about topological groups and uniform spaces that I'll come back to. Then we introduced the space of continuous maps from the topological space X into real numbers. And the X that we will most often take is a compact metric space. And on this, there is the sup norm. We define the supreme norm. And perhaps I didn't talk of these things. In that case, I have to talk about them again. Okay. The last thing last week was I introduced the projective plane as the quotient of the sphere by an equivalence relation under which any point on the sphere is equivalent to its antipodal point. So point in Mumbai is perhaps equivalent to a point in Brazil or somewhere like that. I don't know. And the quotient space is the projective plane. Now, any one-dimensional linear subspace that is a line such as this intersects the sphere in exactly 2 points. So the equivalence classes are in 1-1 correspondence with all lines passing through the origin. So this projective space is the space of all lines in R3 passing through the origin. In general, if you are Rn, you can take all lines in Rn through the origin, and that will be projective space of dimension n-1. Dimension is reducing by 1 because this whole one-dimensional L is becoming just a 0-dimensional point and its other point, which are together a single point in the projective plane. So dimension is reducing by 1. Whatever dimension means in this context, which we have not taught you. This quotient can be thought of as this group action. And now you know this quotient is Hausdorff because this equivalence relation you can check is closed. Okay, so that was the last lecture, and now we are coming to today's material. So before I begin on today's material, any questions? Okay, so now I have a question to you guys. I am curious. Now that we are in the 5th week, how are you guys feeling? Tired? Bored? You have digested everything? How is it going?
I like it, sir. It's a very different way from how I had done these things. I mean, looking at it categorically, I like theories.
Okay, good.
Sort of fun for me.
Thank you. So if you are enjoying it, that makes me also happy. Now, today's material is very standard, and its treatment also is very standard. But it is part of your syllabus, so I am constrained to admit it. Though I am very eager to go to very interesting material involving proper maps, which hopefully I will begin on maybe tomorrow. But then there will be some other leftover material from the syllabus on which I'll have to take a lecture at some point. Okay, all right. So let's go ahead with today's material, which is, so let's look at these spaces CXR for compact Hausdorff space X. It has sup norm. So I keep talking about sup norm. I hope everybody knows what is sup norm. Okay. So let me draw a picture to explain to you what is sup norm. So I'll take this space, C01, that's the best space to take. So then I'll draw the graph of a function. Of course, the function is bounded because it's continuous, and so the graph will fit in this little rectangle. And this is how the graph may look. So what is the sup norm? The sup norm of F is the supremum or maximum, actually maximum is achieved, maximum of mod f x for x belonging to x. That is the sup norm, very simple. Take the maximum value that the function mod fx takes. And this gives a metric, and this is very easy to check that this formula defines a metric. Now, this is a caution I am giving you because I heard a student asking this in a tutorial, so I thought other students may also benefit. You see, if there is really an inner product on a vector space, so suppose I have an inner product. For example, u dot v equal to sigma ui pi, that kind of inner product. Suppose it's there. This is the inner product. Then there is a corresponding norm, and then one defines the norm of v to be the square root of v dot v. Now, whenever one has a norm which comes from an inner product, the inner product can be recovered like this. If I take u dot u plus u dot, okay, sorry, u plus u, correction. If I take u plus v dot u plus v, that is u dot u plus 2 times u dot v, that's a commutative thing, plus v dot v. And that leads to the formula that u dot v is equal to norm u plus v square, which is what this first term is. This term is norm u plus v square. This term is norm u square. This term is norm v square. So solving, it becomes u dot v is equal to norm of u plus v square minus norm u square minus norm v square divided by 2. So I can go back and forth between this inner product and this norm. Okay, the norm is given by first norm u square equal to sigma ui square, the Pythagorean formula. So you can go back and forth. But it's possible to have such a norm with its properties that this defines a metric. Norm has certain properties, and those are norm u greater than equal to 0 and norm u equal to 0 if u equal to 0. This is first property. Second property is the triangle inequality. It says that norm u plus v is less than equal to norm u plus norm v. And third property is linearity with respect to scalar. The norm of lambda times u, where lambda is a scalar, is equal to mod lambda times norm u. These properties you can see are satisfied by lengths of vectors. And such a function on a vector space is called a norm. And once you have a norm, you can define a metric as the length of the vector f minus g. This norm is the length, norm of f minus g. Now this formula sup satisfies these properties. The formula that we have defined for norm f equal to max this has these three properties. You can check. So it is a norm. but it does not come from any inner product. If you try to define something like this, it does not have the properties of dot product that you would like. All this is provoked by student curiosity. So if those of you who have already heard of inner products, etc., will appreciate what is being said. Okay, any questions on this? So we have norm, but I am not saying that we have some inner product which is giving this norm. Now I want to show you how in this norm a ball looks. You see, whenever I have metric space, you should ask how does a ball look. For example, if I take R2 and if I take the norm, if I take R2 and if I take the norm U equal to mod U1 plus mod U2. You can check this is a norm. You can also check that, but this doesn't correspond to an inner product. With this, the balls look like this, interiors of a rectangle, of a square like this. Another formula is max of mod U1, mod U2. With this, they look like this. This also doesn't correspond to an inner product. Now with sup norm, I want to know how. So if I take sup norm, I take C01. This C01 is the short form for continuous functions from 0, 1 into R. So how do the balls look? I want to know. And I'm going to draw the picture. So this is 0, 1. And on this, I have some function. This function I'm going to draw by green. Here is a function. This is my f. And what I want to know is how does the ball, whose center is f and radius is epsilon, draw. And I'm going to draw it. And it will look like this. Okay, this is how the ball looks. Now let me draw some other function which is in this neighborhood. So suppose I have another function which looks like this, whose graph looks like this. This is G. Then G belongs to this ball. You see, so I should show what is epsilon. This width is epsilon. Okay. This vertical width is epsilon. So any function whose graph is everywhere within epsilon of this f is in this ball. So you understand how the balls look. And now you will be able to see, you already know the definition of uniform convergence. So now the following exercise will make sense to you. Exercise. Convergence of a sequence F1, F2 in C01 is uniform convergence. Of the sequence. Meaning you write down the definition of convergence of a sequence for this metric, and that is the definition of uniform convergence. If you don't remember the definition of uniform convergence, if you write that out, you will get the definition of uniform convergence. So this exercise is nothing but reminder of the definition. Okay. All right. Now I want to ask you another exercise. Do you know this space is complete? Do you know this CX is complete? Yeah, any answer? Is this metric space complete? What do you think?
Yes, sir, this space is complete.
It is complete. And why is it complete? Loudly, a bit loudly, please.
Sir, I have studied in my master's course. I don't know the proof.
The reason why it is, you're right, it is complete. Your answer is correct, it is complete. The reason it is complete is real numbers are complete. So you see what is happening. Okay, so I'll explain the reason to you.
Yes, sir, I immediately recalled the proof.
Very good. Okay, so we will see that in a moment. So today's main theorem is the Ascoli-Arzela theorem, which says the following. Let X be a compact metric space and F a subset of Cx, a set of functions into R. You can take it into C, doesn't matter. Give it the soup now. Then F is compact if and only if F is bounded, closed, and equicontinuous. This is the theorem we want to prove. In the course of that, we will see why it is complete. Hello? Yeah?
I've got a proof for the completeness.
Yeah, but if you wait for a moment, we will come to that point.
Okay.
So proof. Suppose F is compact. Okay. Then we want to show that it is bounded, closed, and continuous. Why is it bounded and closed in CX? Because in every metric space, every compact subset is bounded and closed. You remember this, that in every metric space, every compact subset is bounded and closed. Yeah, we have proved it last time. And why is F equicontinuous? This is by the epsilon by 3 argument. This epsilon by 3 argument takes place all the time. So let us see the opportunity. Let's take this opportunity to understand epsilon by 3 argument. It goes like this. As F is compact, it is totally bounded. So given epsilon, there exist finitely many points. Points are functions. Points of F are functions. So that the open balls of radius epsilon by 3 centered at the Fi cover F. You don't have to think that these are functions. Just think of them as points of a metric space. And that metric space is compact. So it's totally bounded. So they are of any given small size. There are some finite many balls which cover it. Because take all balls of radius epsilon by 3. It is compact. So all these balls, selection of these balls definitely covers it, because each function is it at the center of that ball. And so it has a finite subcover. So finitely many of the balls cover it. Okay? So this is okay. Now every Fi is a continuous function of compact metric space, so it is uniformly continuous. That we proved last time, that every continuous function on a compact metric space is uniformly continuous. And therefore for each Fi there is a delta I such that whenever distance between x and y is less than delta, then the distance between Fx and Fy is less than epsilon by 3. This is the distance in R. We could have taken maps into any metric space, and then here we will write the distance in that metric space. So it's less than epsilon by 3. This epsilon is independent of x and y. All that matters is they should be within that distance, because F is uniformly continuous. And now take the minimum of the delta i's. Okay. And now, can you complete the argument? So now what do I have to show? So here, I have that F(I)x minus F(I)y). So I want to show it is equicontinuous. So what do I have to show? So I want to show that I want to say that this is tiny. And I want to conclude that this is less than epsilon. So can you make an argument? This Fx minus Fy is less than or equal to this. This is triangle inequality. And this is less than this is less than epsilon by 3 because F is in the tiny ball around Fi. This is less than epsilon by 3 by the uniform continuity of Fi. This is less than epsilon by 3 again because Fi and F are within that tiny, F is in that tiny ball around Fi. So each term is producing 1 epsilon by 3 together epsilon. So you understood this argument? To go from Fx to Fy, we went from Fx to Fix, then Fix to Fiy, and then from Fiy to Fy. For that, we had to find an Fi nearby F. So these two were close together, these two are close together, these two are close together. So these aren't too far. Things get added, so you better keep each one of these at epsilon by 3. So the answer is epsilon. So have you guys understood the epsilon by 3 argument? It's a very simple argument. You follow? Okay.
Yes.
Yes, good. Now we want to prove the converse. Let F be closed, bounded, and equicontinuous. Why is F compact? So somebody, perhaps it was Ishan's voice, wanted to tell us why the metric space Cx is complete. Bolo Ishan.
Yes, you take, okay, you have the sequence of Cauchy functions, and their point.
What do you mean Cauchy functions? You have Cauchy sequence of functions is probably what you mean.
Sorry, yes, I find, yeah, I'm not used to speaking, sorry. Yes, you have a Cauchy sequence of functions.
Yes.
And they're pointwise Cauchy, so
yes.
the pointwise limit exists.
Yes.
And since this, so all you have to do, and this is on a compact space, so the convergence is uniform.
Yes.
And sorry, 1 second.
What do you want to prove?
You have to show that this is now finally continuous.
The limit, the pointwise limit is a continuous function.
Yes, yes. And what you do is, okay, just 1 second. So let the fn's let's call them fn's, okay,
Yes.
and they converge to some f,
Yes.
and I want to say that the f itself is continuous.
Correct.
So what you do
Yes.
is, let's say some epsilon is given, okay,
And you make an
and
epsilon by 3 arguments.
yes. That's
Okay.
hmm,
So which is why I delayed this till the epsilon by 3 argument is shown. Yeah. So
yeah.
same, the argument is going to look like this. This is the argument. What Ishan is saying is that you want to show that f is continuous. The distance between fx and fy is tiny when x and y are close. But f is the limit of fi. And so this distance is tiny. This is tiny because each one of the fi's was continuous and uniformly continuous for here. And this is tiny. So again, you make an epsilon by 3 argument suitably changed to this situation. And you conclude that the function f is continuous because fx minus fy is smaller than epsilon when x and y are within delta. Okay. So here, of course, I must say, I forgot to say, okay. So complete, that's okay, by an epsilon by 3 argument. Now, so this didn't really use anything about 0, 1. If X is any compact Hausdorff topological space, then Cx is a complete metric space that you can prove by the same argument again. Instead of mod this minus that, write, yeah, you can still write there and write distance instead of, yes. So we have written it as if we are working in that situation. We have never used the metric on X in any of these arguments here. Epsilon by 3 argument. The metric was used in this balls and whatnot, that you don't have to use. So this proof is just this proof. This proof is this proof. It doesn't use X to be metric. And so the proof went by showing that the uniform limit of a sequence of continuous functions is a continuous function. That was epsilon by 3 argument. And now deduce it is complete. And the main ingredient, as Roshni answered, was that R was complete. That's why the sequence of values had a limit. You could define a pointwise limit because the pointwise sequence being Cauchy, a sequence of real numbers, had a limit. Okay. Now we want to show that f is compact. And the metric space is compact if and only if it is complete and misprint. Complete and totally bounded. So we just have to show that f is totally bounded. Now, as the first step, I'll show that f is uniformly equicontinuous. Do you remember the definition of uniformly equicontinuous? Most of you do, but just to be on the safe side, uniformly and equicontinuous. This uniformly means epsilon does not depend on x belonging to x. Equicontinuous means not epsilon, it's called delta. Given epsilon, delta does not depend. And equicontinuous means given epsilon, delta does not depend on f belonging to f. Uniformly equicontinuous means given an epsilon, you can choose a delta independent of x and independent of f, such that distance between x and y is less than delta, implies distance between fx and fy is less than epsilon. Okay. These are very much metric space notions, uniformly and equicontinuous, because they involve this inequality here. Okay. So step one in the proof that f is totally bounded is that f is uniformly equicontinuous. So let us show this uniformly business by similar inequalities, not epsilon by 3 this time, but an epsilon by 2 argument. So given epsilon greater than 0 and given x, there exists delta x, such that distance between y and x is less than delta x, then fx minus fy minus fx mod is less than epsilon by 2. Why? Because I know, yeah, why do I know this? Because I know it is equicontinuous. So here I must write in red that for all f, this is because of equicontinuous. Because of equicontinuous, this means for all f, this inequality holds. Equicontinuity is this. Okay. Now, by compactness of x, there exists some finitely many x1, x2, xn such that these balls, but I'm going to take balls of half the radius, you will see why. So that the balls of half that radius cover x. These are open balls of radius half of what is required here. Why half? Because if I have 2 points in that half-sized ball, 2 other points, P and Q, then the distance between P and Q is that number delta. Diameter of that ball is as far as 2 points can be. Radius is half of how far 2 points in a ball can be. 2 points in a ball can be as far as the diameter almost. Okay? But for the inequality, less than. So if you take a ball of half of what you want as radius, then the size will be what you wanted. And that is why I think the ancients defined pi as circumference upon diameter. Why didn't they define it as circumference upon radius? Because for them, the size of a circle was the diameter rather than radius. How large is a circle? Oh, well, how wide is the circle? That is diameter, not radius. Radius is something which only mathematically educated people start talking about. For a common person, size of a circle is its diameter or perhaps circumference, but not radius. Okay, so you take this half-size ball, so its width is given by this delta x. Finitely many cover. And now take the smallest size among those. Call that delta. Now suppose 2 points are within that delta by 2. Now choose one of the points x size so that x is in one of these balls, which means because these balls cover x. So distance between x and x is less than delta xi by 2. I could have easily called it delta I anyway. So distance between y and xi is distance between y and x plus xi less than equal to is less than delta xi because each is half. And so distance between fy and fx is less than equal to distance between fy and fxi plus distance between fxi and fx. You want me to write it in that order? It is symmetric. It doesn't matter, but to make it look very uniform. Let me write it in this map. Okay. And that is less than epsilon 2 plus epsilon 2, each is epsilon by 2, and together it is epsilon, that's QED. So this family is uniformly equicontinuous. What we only began by saying is equicontinuous has turned out to be uniformly equicontinuous. Any questions on this step? Because now the last step is going to be shown pictorially and your job is to write down the proof in notation. Notation can get ugly. The pictorial idea is very simple. So again and again we have encountered two kinds of arguments in this course. One in which the argument is very categorical based on universal properties. Second is where the argument is very pictorial. The categorical universal property argument is very easy to write down formally. Its formal steps and decomposition into steps is pretty obvious. The pictorial argument is very easy to grasp intuitively if you get the picture, but writing it down in notation takes some effort. And generalizing it requires some imagination. Its formal properties are not as good as those of categorical arguments. So this F is totally bounded. I'm going to give you a pictorial argument. And your job is to convert the picture into notation and return proof. And if you don't succeed in doing that, look at any textbook. As I told you, this lecture is a very standard one. There's nothing different in it than what is there in all books. So let me go ahead with the pictorial argument. But before that, is this point clear? Uniformly equicontinuous. Bolo. Okay, since there are no questions, it is clear. So now I'm going to show that F is totally bounded. So I'm going to draw a picture. So I'm going to draw a picture taking my X. Let's see how much space I have here. I'll take my X to be here. This is X. And this is my R. It could have been any metric space which is complete here. Any complete metric space would do. Okay. Now I have family of functions F. F in Cx is bounded, which simply means that there are two values because as you know, the sup norm takes the supremum of functions. So because it is bounded, norm F is less than n, let's say. Then you simply take the interval 0, minus m, plus m, and all graphs are going to be within that because the norm is less than n. Yeah. So I might as well take maps going from x into this interval minus n. Imagine this interval. And this interval I am going to cut up into tiny pieces. And these various values I am going to call as the AIs. A1, A2, A3, AN. And I have cut it up into tiny pieces. What if it's a complete metric space Y? Then I have AIs belonging to Y such that balls AI epsilon cover Y. Okay. For any epsilon, I have some finitely many such AIs such as these balls cover Y because Y is totally bounded. Why is Y totally bounded? I have replaced Y by a certain bounded subset here. Okay. So you can focus your attention on R to begin with and simply think of these points AI as uniformly chopping up this interval. This argument can be translated for any complete metric space by replacing this chopping into tiny intervals by covering by tiny enough balls, finitely many balls suffice, blah, blah. Okay. So here you can better still, take this to be a compact metric space, any compact metric space. For R, I have taken my compact metric space to be minus m to n, because mod x is less than n, norm x less than n. And in X, I again choose large number of points, x1, x2, x3, x4, x5, blah, 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 blah. So that any point of X distance, so the balls at xi of size, let's say, delta, cover X. Okay. And now I'm going to consider points at the intersection, points of this kind. x1, a1, x1, a2, x1, a3, x1, a4. I have this large number of points. Typical such point is xi, aj. Look at these points. I have a large number of these points. Now I'm going to define certain neighborhoods. First of all, I'm going to think of functions, and these are very funny looking functions. There may not be such functions after all. Okay. Think of a function which says that f at xi is alpha j. Think of these functions. So I produced a whole lot of functions, you see. Understood? I have produced a whole lot of functions. And I am going to say that these functions are going to be such that every function is going to be close enough to them. These are going to fill up my space of functions. I want to show that this is totally bounded. Okay. So I'm going to basically show that if I take functions on X whose values are in minus m to m, these functions fill it up very closely. Every other function will be within a tiny neighborhood of these functions, and which is why the space of functions from X into any interval a, b, which for us here is minus m, m. This is totally bounded because I produce all these functions and they're going to be the centers of balls. So for that, I have to write an inequality. So if I have any such function, and let me call one such function alpha, okay. There may not exist such a function, by the way, but that, so think of alpha as simply a map from x1, xn, over. Have I used the same notation here? Xn. To a1, an. I may not be able to interpolate it and make it a function from all of x. This is just a dot function, only from this subset to this subset. Now, I can define a neighborhood U alpha. U alpha is going to be the set of all f in F such that f of x I minus alpha of xi is less than epsilon for all I. So I can adjust this. I may have to adjust this epsilon to epsilon by 2, epsilon by 3, epsilon by 4. I think I'll have to adjust them to epsilon by 4 because I have also read the books once. And then with this adjustment, one can show that every function in F is in one of these balls. So one can show that the U alpha cover F. Okay, and this is the argument for total boundedness. Okay. Okay. So to show that this U alphas cover even any function f, I want to show that it belongs to some U alpha, right? Either U alpha is empty or it belongs to some such U alpha. Okay. So because the AIs, because the balls around AIs cover the space minus m to m, the balls of radius epsilon, the value of f at any xi is close to one of the AIs, some one of the AIs. So choose one. For every xi, you choose some aj, such that the value of f is within that distance of that aj. And so for x1, that may be a something, for x2, that may be a something else, and so on. And that defines a function alpha. And then by definition, f is in the corresponding U alpha. So these U alpha sets cover it. What is the size of any U alpha? Okay. So if I any two functions in U alpha, then at your checkpoints, their values are not very far from each other at the checkpoints. Can they be very far anywhere else? No, because all these are uniformly continuous. And any other point is close to one of the checkpoints. So again, an epsilon by 3 or epsilon by 4 argument will show you that the value of these two functions at any nearby point also cannot be very far. So the radius of this U epsilon will turn out to be probably 4 epsilon, I think. 4 epsilon or even 5 epsilon, depends on how you write the inequality. The reason I am telling you all this pictorially is now go and read the proof. And in my tomorrow's lecture, I'll write down a proof. So now you go and read the proof and then try to understand it in view of this picture. If you don't have this picture, you can understand the proof line by line, and then after you close your book, it all goes up. If you understand this picture, you can reconstruct the inequalities by yourself. So which is why I am taking this approach of showing you the pictorial argument, which gives the various formally written proofs in the books. Okay. So this is the end of my time, and so all of you are now going to honestly spend 1 hour struggling, and you should be able to get it in 15 minutes and not 1 hour, converting this pictorial argument into the proof of total boundedness of F. And I will stop here and ask